Good. Well, thank you. Welcome back, everybody. I hope you're making good headway on the tutorials. Um, this one gets down to kind of a lower level of Kineros parameters and input files. So basically, as Shay said, AGWA creates all of these files. But if you want to get down to a lower level and change things within Kineros that AGWA can't do, this presentation should show you a little bit about how you can do that. So there are three main input files: a parameter file, the rainfall input file, and a run file, which is optional because you can hand enter some of the run file information. So these are just ASCII text files, and you can create and edit those just with Notepad or with Word if you, of course, save it as a text file. So the structure, in terms of how you would set up the model elements, you've got a global block, and then you're going through element by element. So each element can have different infiltration, hydraulic resistance parameters, different soil parameters, etc. So there's some parameter file tags, which can be used to either enter things in lists or in columns. So for example, if you're looking or entering volume or discharge, you can enter it in a row as shown under lists, or in a column as shown at the bottom. So the tags will be recognized typically by the first three letters. So you don't necessarily have to type out the whole word. And I should point out that there is a Kineros 2 website, and I'm just looking to see if that's also on our list of links. Not sure I see it, but at any rate, that will also have documentation on all of these files and the variables that are used, as well as the background theory in Kineros. So if you want to add information about comments, the file, the watershed name, etc., just precede it by an exclamation point. And that can go at the front end of the line in the ASCII file, or in the middle, as we see the exclamation on volume, discharge, and then internal note from table 4.1. So the parameter block files are very similar for both channels, ponds, pipes, urban, inject, adder, diverter. So all of the different types of elements are listed at the bottom, and you do a begin channel and an end channel, and then the parameters are listed in between. So in the global block file, you pick units that will be applied to the entire run. CLEN is a characteristic length that helps set up the number of computational nodes for the different elements. And 10 is a good number. And the model will also cut down the time steps if the characteristic lengths and the nodes spatially are too far apart. And channel rain and precipitation rain. So we're not going to put rain on the channels. And we're not going to put rain on, I'm trying to remember what P rain is on the plains. And this allows you to potentially isolate certain elements if you're debugging and trying to figure out where response is going on. So here's watershed 11 again that we saw yesterday. And again, this in this case, we are modeling, remember that pond element was right in here and we sort of cut that off. But in this case, we are treating all of the elements and not going through to cut off the inflow from the pond. So again, there are two basic elements or configurations that make up a watershed. We have the first order channel with one upstream area plus two lateral areas. And again, you basically see that at the end of any first order channel. Here's your upstream area and your two laterals. And then we have higher order channels with two streams joining and two lateral areas. And that's what you see here in the pink area. You have two first order channels that are going in to the upstream part or link of the second order channel. And again, it's two orders. Now, the computational order is important. And again, AGWA takes care of this for you, but you have to basically make sure you're doing the computations in the you basically from the outline of the watershed, the ridges of the watershed, and work your way down. So, if you put these two first and this channel first and don't do any of the computations in the first order subwatersheds, there's no upper boundary condition here to have you carry on the computations downstream. So again, first order computation, we've got our elements numbers here. And again, this gets abstracted as follows in terms of they're represented as planes here, but as we talked about before, they can be curvilinear, they can vary in width from fatter at the top to skinnier at the bottom, and vice versa. And just a point here, the plane widths do not have to be equal to the channel length. Now, Shay said yesterday, AGWA makes that assumption, but you don't have to. And then the, again, default is a trapezoidal channel. What's input into the parameter files is this bottom width. And then again, a side slope on each side of the channel is assumed to be 1-to-1 in AGWA. And again, you have control over that if you want to change it. So here's, what the block structure looks like in terms of the elements. So the first one we're going to compute is a plane, element 51 over here. And, we don't have, in this one, we don't have any infiltration parameters. So it's going to model it as an impervious surface. So we have length, width, slope, and Manning's end. And so we're done with that 51 element. And now we're going to go down to 52. Again, it's impervious. There are no infiltration parameters. Now we'll go to 53, same sort of thing. And now we're going to do the channel element. So what's important is that you have to know what's upstream of the channel element, number 54. So what's coming in from above is 51. So, and what's coming in laterally are 52 and 53. So this now it knows that the channel is looking toward the output of 51, 52, and 53. And again, you can see here, we're modeling it as an impervious surface. So infiltration parameters. If you're doing the old, well, not the old, the 3-parameter Smith-Parlange infiltration equation, and these are explained and there's references for them in the documentation. you're going to input all of these parameters. However, if you use REM, you're just putting in KE, which is a function of some of these parameters. But here they're listed: rock content, pore size distributions. In terms of initial saturation, in other words, how much of the pore space can be filled with water, you typically can't fill the pore space to 100%. And there are tables for these values by soil texture. So there's often an S max, and then there's often a minimum fillable fraction. In other words, unless you put the soil in an oven and dry it out and drive out all of the water in the sample, there'll be some minimum pore space that just will typically not drain out because of the strength of the suction terms. And again, the initial saturation is between these two values. Alpha, again, controls the wetting front transition. Again, this is explained in the documentation. If you want to represent small scale KS variability, you put in a coefficient of variation of KS. Now it's defaulted to 0. We're defaulting S max to 0.95. The residual, again, can be estimated from other parameters. This term, the alpha term, which is a balance on one extreme, is the green amped equation, and on the other extreme is a Parlange infiltration equation, and this basically tells you how the two are mixed. Now, erosion and sediment particles. Again, we're going to have 1 to 5 particle size classes. And in the global parameters, you're going to specify the particle diameters, the particle densities, and the water temperature. So again, this affects the viscosity of the water and therefore how the particles will settle out. Element parameters, we need a fraction of each class. They sum to 1. So if there's 3 particle classes, and 25% is the smallest one, and let's say 50% is the median one, and another 25% is the highest. Again, those have to sum to 1. PAVE is a percentage of non-erodible fraction of the surface. No, I'm sorry, a fraction instead of percentage. So, if you've got rock or erosion pavement or concrete or something that is not going to erode, this is where you specify that. Cohesion, again, hydraulic erosion coefficient, and a rain splash term. Again, this is K omega when REM is used, and this is KSS, sheet splash erosion, when REM is used. And again, these terms that you see here are used in both planes and plane and channel elements, I'm sorry. We can have rainfall interception parameters. This applies only to overland flow or plane elements. And basically, what's the depth of intercepted water on the vegetation and what fraction of the surface is covered with a vegetation canopy. And the rainfall intensity is reduced by 1 minus the canopy until the cumulative rainfall depth equals the interception depth. That's how it's taken out. It's not just chopped off the front end of the HIETA graph, but basically reduces the intensity for this time. So rainfall file, same structure and tags as the parameter file. you can have multiple rain gauges or blocks. Block names are again supplied by the user, rain gauge 1, 2, etc. Now, multiple gauges requires an XY coordinate for the location of each gauge. And this can be in any coordinate system as long as they're in a consistent projection. And again, AGWA, if you have more than one rain gauge, AGWA does this for you. The initial saturation can be specified for each rain gauge, and then that can also be interpolated to each of the elements. So if for some reason one part of your watershed got a recent storm, elements affected by that storm, you might set the SAT to a higher value. And again, this will get interpolated by that space-time interpolation scheme. And if the SAT is specified in an element, it will override the interpolated value. So again, we've got our rain gauge name, initial saturation, and this is the number of time depth pairs. So, exclamation, a comment to say this is in minutes and millimeters, and then you'll have 7 time millimeter or time depth pairs to say how the rain fell during that storm. Then there are a number of print options that can give you greater detail on the outputs. So you can, again, get into real great detail for every element, or you can have an event volume summary. So this is over the whole watershed. Both in millimeters and cubic meters, we have the volume of rainfall that fell onto the watershed. Then we have the abstractions. We've got the amount of water that infiltrated in the overland flow elements and in the channel elements. And then we had a little bit of water abstracted by interception. And storage is basically the amount left on the surfaces of the watershed. And if you see a high storage term, it basically means you're not running the simulation long enough to either let the water come down and flow out of the system or infiltrate. And then this is the computed runoff. And both on a element and a watershed basis, we always do a volume balance. And again, we're volume in minus volume out minus storage. And we want this value to be low, and ideally less than 1%. If this is over 1%, there may be a problem with not getting one of the elements ordered correctly. And this is never zero because of the numerical approximations for the finite difference equations. And this says, well, we put in a time step of, let's say, 5 minutes. But this says the time step was adjusted to meet the current condition. And again, this is a condition that we want to observe and maintain. And again, this affects the potential error in the numerical analysis. So here's the total watershed area. Here's the sediment yield out of that watershed. And then here's the sediment yield by the 3 particle class sizes. In terms of, here's our size of the particles, the top line. Here's our yield in tons per hectare and a percentage of the total. And again, these have to sum up to 1. Okay, if you want to get more details on a particular element, you pick print equals 1. So again, this is in these values are in the parameter file, and you say all right, I want to see details on this particular element because, check it more carefully. Something's going on. So for plain element 11, you see it's got a smaller contributing area. It's a part of the overall watershed. It's telling you what the initial water content is, the estimated wilting point, field capacity, and what is the coefficient on that 3-parameter infiltration equation. And again, this is defaulted to 0.8. It'll tell you the peak flow rate on that element and at what time it occurred. And again, similarly for sediment discharge. And just like before, we're going to do our water balance on the individual element. We get a computed error down here. And we also do a sediment balance. This one, trying to think, this one, you can, on the element itself, you can have both erosion and deposition. So this is sort of basically saying that, there's no element above element 11, so there's no sediment coming in. And all the sediment that was eroded went out of the element. That's why we have 0 deposited. And then so we've got soil loss from the element itself, and that's the equal to the total output. So if you do print equals 2, now you get kind of all the gory details. And this is where a file you would want to say, all right, I want to plot the hydrograph, either for the watershed or for a particular element. So you can see our computational time was set to 1 minute. It shows the rainfall intensity, the outflow out of that element, both in intensity or rate per time, as well as volume per time, and the total sediment. And this will continue until the whole event is over to the final time of the simulation. And in this case, you get the detailed printout, but you can also specify that output goes to a file. So this automatically creates a CSV file that you can pull into a spreadsheet. And again, it's got the labels on top for the first 2 lines, and then all of the same quantities that you saw in the prior slide. It's just put out to an external file. So your run file takes these different files and puts them together to create an executable run. So we can do a batch mode, as in AGWA, or in a prompt mode where you're entering the file names. So in the batch mode, the executable for K2 is always labeled as K2.exe. And then from a command prompt window, you can say, again, the start menu, all the programs, accessories at the command prompt. So, here's one way to look at that. So K2, the executable, -B means it's a batch file, and the files, parameter file, input file, are in a kin fill file. And this way you don't have to type in the names of the parameter file and the input file. So double clicking K2exe from a file browser like Windows Explorers will give you the prompt mode. So you go into the old DOS command window, basically, and you would type in those file names. So in that run file, if you want to do batch mode, This file, again, would just look like this. It's an ASCII string. It says, all right, here's the name of the parameter file. Here's the name of the rainfall file. And we usually use a PRE, precipitation extension on this. And here is the output file. And we use .out typically. If you want to associate a particular title, saying event November 14th, 2002, you can put that into the double quotes. And again, this is the duration of the run, 120 minutes. Here are the time steps. Here is the current adjustment. And I would suggest you always answer to this. Is there sediment included? Again, if you have erosion and sediment going on, this is where you would say yes. And then a multiplier file. And we don't have one in this particular case. We'll show you what that does in just a minute here. And then do you want a tabular summary? That's yes. So the file can have, again, multiple lines, multiple events in it. It's sort of like imagine the AGWA case where, you do a run, you save everything. And so then you want to do another run and difference it. Well, everything is saved from the first run, file names, output, etc. This allows you basically not to have to re-enter all of the file names. So what's a multiplier file? This is the case where, and we use this in calibration typically. Instead of trying to change the saturated hydraulic conductivity on each individual element, we're assuming that the relative spatial differences in KS are captured by the soils data and the land cover data. So we're just going to scale those relative differences up or down. So a multiplier can be below 1 if you're going to scale those down. So if you're producing not enough runoff compared to the observed case, you would use a KS multiplier, typically less than 1. Okay, so we have similar multipliers, again, for Manning's or the Shezzy. You can use either one of those. For the coefficient of variation, the capillary drive term, and that has to do with the initial suction abstractions, interception, and then again multipliers for the cohesion term and the rain splash parameter. And again, these, as noted, the multipliers are applied globally, both to planes and channels. Okay, so here's again the Kinneros website. It describes the documentation. And so on this side, it talks about the model components and what is in the parameter file for each of these types of processes. And, then it talks about, what are the input parameters, and what do they mean? And in this file, or over in this is basically the, kind of theoretic background of how we're representing things like routing, infiltration, and erosion. So that site is here. If you just Google Kinneros 2, you'll come to the right site. You can also get the source code, and you can download a PDF of the current documentation, and you can also download a 1990 manual that was first put out, that was scanned. And this has some good information in it. We've tried to capture all that information in the current documentation, But, some people still like the 1990 manual. So why would you want to work with Kinneros outside of AGWA? Automation, so is one. So how do we want to run, or we can run Kinneros from other programs or scripts that will allow you to run multiple events in a batch mode? Or for example, you could put the Kinneros, run Kinneros with a program, an outer loop program, like you would PEST to do parameter optimization, where, those multipliers would be changed as a function of what comes out of PEST in terms of moving to try to get a optimal file. And then we want to also potentially insert elements not supported by AGWA. And that might be storm sewers, inflow via a injection element, or a composite urban element. And the common one is incorporating cascading overland flow or plane elements. And again, we had one graduate student to try to look at the characteristics of the topography and the land cover to say, well, should we really break this thing into a separate element and have two elements instead of one? And we really, I don't think, and Phil can tell you more, but we didn't really come up, I think, with a satisfactory rule-based procedure to break these up. So this is, again, something we don't do in AGWA because we didn't get the intelligence, if you will, in the programs to do this. And again, this is, I guess, a best decision by the user based on the conditions you see. We have a pond block or a pond element as well. And basically you need a relationship between the surface area and volume as a function of how deep the water is in the pond, and this is typically done with a field survey, or you can, we found that you can do this with good LiDAR. So again, that's got a number. It's getting inflow from element number 6. We're going to use the simple print option. Again, we want to know where that pond is in terms of how rain will go on to that. We've got 12 lines describing the volume, discharge, surface area. And initially, it's starting out with 0 water in it. So, as this thing fills up, you get to a point where the pond will spill. So you need to know, is there some control here or a weir to basically say, well, what is the discharge if the depth of water over that control element, let's say it's a weir, what's the discharge when there's X amount or X, millimeters of depth over that weir? So here we can see there's really, minimal discharge from these until we get up to this level. And then we start discharging, and typically then the surface area will stabilize as well. Oh, and again, infiltration, it's not shown here, but you can specify infiltration parameters for the pond area if it's a natural surface. So there's the urban block. Again, Yoga will show you more about the urban tool that is a part or an add-on to AGWA that basically does this and does it in a more sophisticated way. But again, this is, you can specify how much pervious area is directly connected to the street, impervious, and then the various combinations of runoff, run-on. And again, for the urban block, then again, you'll have an ID. If you say 0, you're not going to get any printout. What are the characteristics in terms of overall length and width of that urban element? And then now you've got multiple slopes. And this is typically the slope of the, let's say it's a lot coming in. This would be the slope of the half street channel. And that's across the street. So let's say it would act like a crowned street. And then you've got different Manning's values for different elements or different characteristics. So if I recall correctly, I think this is for the impervious area, for the infiltrating areas, and for the street. Let's see, CS. I'm blanking out on this one. I think this is the slope down from the stream. So, we're assuming flow. Let me go back one. So we're assuming flow comes out of this urban element, goes on to the half street, and then flows down, changes direction. And I think CS is the downslope of the street crown. And we also need a cross slope term. Okay, so here are the infiltration values for infiltrating surfaces. Again, same stuff we need for an infiltrating overland flow element. Interception terms, where's it located, XY coordinates. And now what are the percentages of the directly connected pervious, the directly connected impervious, et cetera. Again, so these have to add up to 1. And again, that's the end or the urban block, if you will. So pipe and inject. If you've got a pipe in the system, we need to describe the pipe in similar cases. Its length, diameter, slope. What's the hydraulic roughness of it? Where is the water coming from? And it's coming from these 4 elements upstream into the pipe. And one thing to note, though, we don't do pressurized flow. The kinematic equations, that's a restriction. You need something like a diffusion equation or a full Reynolds, a full set of the equations that'll handle pressure, heads, and that sort of thing. Now, an inject element, again, this can be inserted anywhere. It has an ID, but if the hydrograph for something that say was measured by a flume inside your watershed, this will be read again in time discharge pairs, and that gets directly injected into any place in the watershed. So again, you have to remember, if you put an injection element in, the element you're going into, you have to name 200 as one of the upstream points that drain into it. So adder and diverter channels. The diverter element mimics what we talked about yesterday in terms of if you want a constructed wetland, you typically will want to divert the flow into, let's say, multiple channels that will, have a slower flow, go through a wetland, et cetera. And again, but you have to specify how the flow gets split up and with the 2 diversions. And again, your upstream input, there's an element that comes into the diverter. its ID is 2. And in this case, we're diverting just to 3 and to 4. And similarly, we can have an adder channel. So the case doesn't occur that much, but if you have 3 channels coming together at one junction, you would use an adder channel. And basically, again, it's taking the discharge from all of these inputs, adding it up in boundary condition for element 4 downstream of it. Oh, and let's see. I guess that's it. So I know that was a lot to digest and a lot of detail. So are there questions? And again, this is all documented on the website, and we can help you, and we've often helped users. If there are bugs or something, and you give it a hard try and it's still not working, you can send us the parameter and the input files, and we might be able to very easily discern, what's going wrong. So that's an option as well. Okay. Oops. Okay, chat window. All right. So where are the parameter block files? You create them in an ASCII file, but okay, Shay has answered this. But they're also created by AGWA. And you can go into them and you can alter some of the parameters. Again, if you have local data, let's say you've done a double ring infiltrometer test on a particular area, AGWA is going to give you that first initial estimate that we talked about yesterday. But that's based on all of those assumptions that we made about the land cover and the soils file. And if you have measured data, that's much better, and you should use that data. Okay. How does AGWA identify directly connected impervious areas from impervious areas? And Yoga's talked about that one. And again, he'll tell you more about that with the urban tool. Okay, unfortunately, we lost a user that's in some time zone somewhere in the world, but they can hopefully view the recording.
Hey, David, I just have a quick question.
Yeah.
Thank you for a great presentation, by the way. But I was just curious. So I know you talked about how running Kinneros outside of AGWA, you can automate it. I was just curious if you have a recommendation for what program to use to run it in the loop, like if you prefer R or Python for this type of study.
I think you could use, anything that will identify the files that you need to see that executes the K2.exe. So we've used Python, we've used C++. Depends on the language either you're comfortable with, or if you get a program like PEST, some sort of optimization program, I don't know what the current language is for it, but that again will execute these. So doesn't have to be, any specific language.
Yeah,
Okay,
the
thank you.
passcode is not available. It's just the executable.
Okay, gotcha. Thank you. I just had one other question. So when you were going through the parameter files and some of the inputs on there, like specifically on slide.
Let's go back here.
Sorry, yeah, I'm going through your slides.
Do you
Like when we're
recall?
looking at like the KS and the G function, is there a way to open the parameter file and edit those directly to put in like a unique value that you want to test?
Yes. So, I mean, if you're just working with the ASCII files, open those with Notebook or, any ASCII text editor. And Shay, are you going to, or do one of the tutorials have a situation? So these things are, I think there's potentially two locations. You can change the parameter value, again, with an ASCII editor. And when all of this stuff is read into AGWA, it goes into tables. And you can access those tables and change it there. And does any one of the tutorials, Shay, show that?
Yeah, tutorial 10, I believe, has you open the parameter files and manipulate those. I think with probably just Notepad from Windows. I mean, Notepad is what comes with every Windows installation, but I'd really recommend getting a more powerful text editor. Whatever that is up to you. But yeah, you can certainly just navigate to where those parameter files are saved and edit them yourself. One important thing to note is that, whenever you do make those edits, if you're kind of running them with AGWA as well for visualization purposes or for, analyzing results, when you do any modification to those files, one, you have to make sure you rerun the simulation, but two, you would also need to import the results again after you've made any of those edits and modifications. Let me just double check that is tutorial 10.
Okay, so you'd recommend running it with the default parameters and then going back and editing them and rerunning the simulation and re-importing it?
Yeah, if you're trying to do some, some calibration, some basic calibration, doing the default run is the best place to start, right? It's like doing all the work for you in terms of creating your input files for you. And, that can get quite cumbersome if you've got hundreds or thousands of elements. So once you have that created, then editing it either through the parameter file itself or in AGWA, you can edit the parameter attribute tables and make the manipulations there so that they're kind of saved. And one thing that we try to do to facilitate that is allow you to copy existing parameterizations and just makes a one-to-one copy of it and names it something else. And then you can that way maintain a copy of the original, and then any edits you make kind of are kept separate from that in the attribute tables. So there's multiple ways of doing it, and it's really what you're more comfortable with and kind of what you think might be the most efficient way to do those manipulations.
Okay, so you can open the .par files in ArcMap and then edit the attribute table is what you're saying as well? That's another
Sorry,
option.
the attribute tables are in the file geodatabase, or sorry, the personal geodatabase that's created during the delineation. So there's several tables in that geodatabase created after you perform the parameterization. So that's where you can edit the attribute tables. The par file itself is just a text file that is not, you cannot open that in ArcMap. That's where you need to use the text editor to edit it.
Okay, got it. Thank you so much.
So just an example in terms, if you're not using AGWA to set up a run, in other words, you're going to create all of the elements you need. A good check now is to say, put a multiplier of 0 on KS. So basically you're running an impervious surface, and then put in a constant rainfall rate for a long period of time. And eventually the output should reach that same rate of rainfall input. And, this is, and if it doesn't, something's not right. There may be a connection, or one element might have been dropped out accidentally by not having the right upstream connections. Now, Shay, if I'm remembering correctly, AGWA does make sure there aren't any orphan elements. Is that right?
I don't think AGWA is doing that necessarily. I think the model itself does that. So it'll actually run without giving you an error. But in the output file, or maybe in the command window that opens when you run the model, it will report that that there is an orphaned element. Now, what happens is if you run with an orphaned element, AGWA shouldn't create a discretization where there's any orphaned elements. But
yeah, that's what I mean. Yeah.
If you make any edits, outside of AGWA or outside of the workflow that is defined and create an orphaned element, if you try to import those results into AGWA, that will give you an error because there's going to be unexpected output, which is basically the warning or the output from the orphaned element. And just to reiterate, I know Dave had mentioned it, but what we mean by an orphaned element is one where the outflow from that is not connected to another element in the parameter file. So it's kind of stands on its own. And I don't know if there's any reason that you would want to do that, but the model won't actually crash if you do.
And another quick check is if you know the overall watershed area that's say been determined by an analyzing a DEM, let's say, or a gauged watershed, all of the USGS gauges do report the contributing area to that particular gauge. And if on the summary output file, it always has the control or the contributing area of the watershed, the whole thing. And if that area doesn't match, what you know of as an independent method of deriving that area, then again, something's unconnected. Other questions? Well, I guess we're up for a break here, aren't we?
Yeah, I'll put a slide up that says when we're returning. But yeah, we'll return for another presentation in about 1 hour.
And one other thought, or one comment I saw yesterday that I thought was very good was having a short break between the presentations. So we have 2 in a row coming up, and we'll have a short 5 or 10 minute break between 6 and 7. Good. Thank you, everybody. We'll see you back then.
Looks like it's about that time. Welcome back, everyone. Thanks for sticking around. We've got Phil giving our next presentation. He's going to go over some of the different management tools that are available in AGWA. If you haven't had a chance to use them in the tutorials that you've been working on. So, Phil.
All right, you should be able to see my screen with the presentation. This is presentation 6. And what we're going to be doing in this presentation is review some of the tools in AGWA that allows you to change the input data to represent different types of disturbances across the watershed or management actions that are occurring within the watershed. Now, excuse me, there we go. One of the reasons why we've developed these tools over the years is because we've worked with a lot of different agencies, okay, in developing AGWA. BLM, the Department of Defense, military bases, NRCS, EPA, their teams in the Forest Service, as well as in the Department of Interior. And so these tools that we've developed have addressed different concerns that they had, okay, related to disturbance. These have 2 slides here, okay, a fire, livestock grazing, as well as incorporating best management practices to try to control erosion or mitigate flood risk. So again, we've developed a suite of tools to address some of these issues. Here's just a list of some of the tools that we've actually developed. I'm not going to go over all of these in this presentation. Land use, land cover modification tool that allows you to go in and change the land use vegetation type within a watershed, either the entire watershed or just a small component of the watershed. We've also worked on using NRI data to characterize vegetation, as well as looking at ecological sites. But basically, the tool allows you to identify an area and change what's there. We have a tool that allows us to essentially incorporate a buffer strip into the model. So we can actually say this length of channel will have a buffer strip of a certain type. So we can actually have different input parameters for that area, that buffer around a stream or a lake or water body. We have another tool that looks at military training disturbance. I'm not going to be talking about that tool, but this is something that you can actually apply where you're running heavy vehicles across the landscape. Now, we were looking at Fort Carson when we developed this tool, so we're talking about tanks, okay? But it can be used in different situations where you're seeing essentially significant amount of soil disturbance. You can incorporate detention and retention ponds into the watershed. We actually developed a tool for doing this, a storage characterization toolkit. You can essentially have multiple pour points within a watershed, or you can delineate an area of concern and find out what watersheds drain from that area or drain through that area. We have a tool that looks at post-fire effects. In the next presentation, Dave is going to talk more about these tools that we've developed for looking at post-fire effects, as well as putting in best management practices post-fire. Okay, I'll have one slide on it in this presentation, but Dave is going to talk about that in more detail. We have developed tools to look at built environments, residential developments, as well as commercial, institutional. All right, Yoga, as part of this presentation, is going to talk about the urban toolkit, and we have a tutorial on the urban toolkit. And then I'll talk a little bit about channel routing, some of the changes you can make there. I already talked about this in the last presentation I gave, but I'll go through some other things that you can actually do. Probably the most heavily used tool is a land cover modification tool. This is where you can actually go and take essentially a polygon that you've created before, like a pasture area, or you can draw a polygon on the screen, and then you change the vegetation type within that polygon, either 100% change, or you can also essentially define a random pattern or a fractal patchy pattern, or specify the percent of successful change within essentially a watershed. Let's say you're going to remove 50% of the mesquite or shrubs in a given area related to a shrub management practice. Okay, so this tool again is one of the more common tools that is used. You can go into your subwatershed. We're looking at an area in this case in the San Pedro Valley. Okay, originally it had essentially two cover types. Now it has one cover type. We changed one type to the other type. Okay, so again, this is a tool they can use. And again, we can actually essentially either change it or create a random pattern of vegetation or a fractal pattern of vegetation within the area of concern. So again, this is a very common tool that we use to change land use, land cover. Here's just an example of that tool at work. We have a small watershed, and we wanted to change the vegetation type from a high plant cover to a low plant cover. And then we essentially modeled the result. So essentially, you can actually say before grazing, after grazing, basically what may happen. And so we're looking at here as a change in hill slope erosion, as well as a change in sediment yield in the channels. And you can see that the high cover had a lower erosion rate compared to, okay, the essentially low cover situation. So again, this is just an example where we went into a small subwatershed and changed the vegetation cover percentage. We actually, in this case, we went from a historic native plant cover, okay, to a mesquite native plant community, which had much lower, essentially, canopy cover, 78% to 25%, and ground cover was 72%, 72% to 40%. Again, this is in Kinneros. Okay, what you can actually physically do is go to a channel system. You have to identify essentially the beginning and end of the riparian zone. Okay, we would then physically break, okay, the hill slope element. So we have a unique hill slope element, okay, for that riparian area. And this is where we're using two planes. We have the upper plane and the lower plane. The lower plane would be the buffer, and you can have different input for these two planes in terms of vegetation cover, as well as essentially the gradient of the slope. So you can actually incorporate, okay, an area with higher cover in the buffer zone compared to the upland part of essentially the plane. All right, and so this again is something that you can essentially use to put in something different along essentially the channel. In this case, we're talking about mainly a buffer. This is another example of using, okay, the land cover change tool. We can incorporate, for example, an urban development within the watershed. That includes maybe potentially changing the channel system, as well as essentially the change, okay, in cover, and that model essentially the result. So in this situation, we had an urban area essentially being proposed within a subwatershed in San Pedro, okay, and then we actually model the potential impact of that development. And you can see down channel of that development, we saw higher runoff rates, as well as higher essentially runoff occurring. You can see the change in colors from essentially very light to very dark. All right, so again, we're seeing an impact of development. So we're incorporating the change within essentially the watershed. In this case, essentially a proposed development. Post-fire effects tool. Okay, again, Dave is going to talk more about this, okay, in the next presentation. So we're evaluating the post-fire effects of a fire. This is a small watershed in Idaho, where we basically are looking at what would be the impact on runoff and erosion, okay, if half of the watershed was burnt and all of the watershed was burnt. Okay, and basically we change, okay, the vegetation based on burn severity, as well as we change the height, essentially the Manning's N value, okay, essentially for the hill slopes. And where you can see that we have the pre-fire situation where we saw very low runoff for a 5-year, 30-minute design storm, okay? All right, 35% of the watershed was burnt in one case, a partial burn, and then 100% of the watershed was burnt. Okay, we essentially look at, again, burn severity in these situations. You can see that the partial case, the only upper part of the watershed was burnt. We saw an increase in runoff, okay, cubic meters per second, approaching 150 cubic meters per second, where before it was basically below 50, very close to zero for this event. And then the entire watershed, we're approaching 350 cubic meters per second. So again, you can see that the fire had a significant impact on, okay, runoff in this situation. This is what we actually use with the BEAR teams, okay, the burn area emergency response teams in the Department of Interior, as well as the Forest Service. Here's an important set of tools that we have. You can have multiple pour points identified, as well as doing a multiple watershed analysis. Now, with the multiple pour points, you can have more than one pour point that you will force to model, essentially to force AGWA to model to that point. Okay, that will be an endpoint, okay, for a sub watershed. So in this example I'm showing you here, we had the main pour point for the entire watershed, and then we had a secondary pour point, an internal pour point that we would model to. The model will break on that point and we get actually output for that specific point. So that could be an area of concern, essentially within your watershed, or it could be an internal gauge site within your essentially larger watershed. And you want to model to that point as well as to the entire to the pour point that represents the entire watershed. So this is an important tool. We use this a lot when we're working post-fire. Usually, essentially a BEAR team will have identified what they call essentially VARs, values at risk, okay? And we will model to those values at risk within the larger watershed, okay? And it will force the model to essentially to provide output, hydrograph and sediment graph for that specific location. Now, the multiple watershed analysis allows you to identify an area of interest, like a fire or an allotment, okay, some type of disturbance, and it will then identify all the drainages from that area, okay? You know, what drains from that area or what drains through that area, the watershed that drains through that area. So again, if you have some type of disturbance like a wildfire, you would identify the essentially wildfire area, okay, and you would find all the watersheds that drain from that area or through that area, okay? Okay, and then you'd be able to identify, you know, which watershed you are interested in terms of that disturbance. Okay, so in this case, maybe this was a fire area and you're actually seeing that essentially we had much higher flows on the west side compared to the east side. Routing tools and options. Dave talked a little bit about this dealing with Kinross. We do have a pond/reservoir tool. So you can actually essentially place on the channel system, a pond or reservoir, and then you basically could model water flowing into the reservoir and out of the reservoir with some type of control structure. Okay, you can also identify an area where you have essentially diversion. In some cases, you may call that an artificial wetland. I'll show you a figure of this in a second. You can actually remove channels. Okay, that does happen with development. Essentially, that you actually will remove channels or replace channels. Some of the natural channels will essentially go away and they'll put in a man-made channel in a development. You also can, and I talked about this earlier, parameterize a channel with the depth essentially values, essentially the hydraulic conductivity of the bottom sediment. We typically recommend, 0 for perennial streams, but you can actually assign what is the hydraulic conductivity of your bottom sediment of a channel. Change the roughness value. Armoring, that's related to the erodibility of the channel itself. It can go to 0 if you want. You can have compound channels. And then again, each channel reach can have unique parameters. Okay. So one thing we've actually developed for essentially putting a pond essentially into a Kinneros setup, okay, is that you can actually identify and characterize an existing structure or one that you are proposing. You can calculate the dam discharge, basically the stage to discharge relationship, okay? And then you can export essentially all that information into Kinneros. So you're identifying where that structure will be on the channel system, and you can identify its storage capacity, as well as essentially create a stage discharge relationship for that structure. Right. Okay. And we have these different essentially pop-up windows where you would put in the information, okay, that you need to characterize the existing storage, or essentially calculate the dam discharge, essentially the stage, okay, essentially discharge relationship, and then where do you want it routed, or essentially where do you want it essentially develop the input file for Kinneros. Here's an example of the tool in use. Okay, we had a point identifying the location of a small stock pond. This was on the one of the military bases in California that we were working on. Okay, so we know the location of the pond. Okay, using the DEM, in this case, essentially a LiDAR DEM that we actually had. Okay, we could identify the storage behind this pond. Basically, it would be the depth where essentially the area that would be submerged before water started running out of it through this emergency spillway over on the right-hand side. Please note that we can actually see in this LiDAR image the emergency spillway as well. So we actually have the storage area behind it, as well as basically essentially where it will flow out of, okay, in that elevation. I might add, this was so high, we can actually get the characteristics of the emergency spillway as well, okay? Okay. And so we have now defined the different features of this pond, okay? Using the GIS capabilities, we have identified basically the amount of storage. We have a essentially depth to storage essentially relationship. We also have developed another relationship. We'll look at essentially the stage to discharge relationship, okay, in this structure. I might add, when you're working in the western part of the United States, there's usually ponds everywhere, especially in rangeland conditions. Okay, they provide water for essentially livestock, they trap sediment, they retain floodwaters. So if you're doing a full watershed assessment, you really need to include your ponds. Okay, and ponds can be viewed as essentially stormwater retention structures as well as sediment basins. Sediment is going to be trapped in these ponds. Okay, and it is a common best management practice for mitigating flood risk as well as water quality mitigation. So again, being able to model ponds, okay, as a best management practice or essentially a current best management practice is really important. And so what actually we're looking at here is what would be the relative difference between, okay, pre and post stock ponds, essentially channel runoff, okay, from this small watershed, which is located at the Walnut Gulch Experimental Watershed. All right, and so you can estimate the pre and the post runoff, the percent differences, as well as the sediment essentially flow coming out of that area. So again, this is something that you can actually essentially do for Kinross. Okay, and I believe for SWAT as well, we can put in the ponds, okay, where they are occurring within the watershed. Okay, diversions. Okay, we can basically divert water out of the channel and put it back in the channel. In this situation, we're trying to represent, okay, a potential man-made wetland. All right, so we have water going into essentially a pond. We can route the water out of the pond through this essentially channel system into another pond, and then model basically the outflow from that pond, and then essentially deliver that water back into the channel. So this is where you can actually represent like a man-made wetland or any type of diversion out of essentially the primary stream. We can have overbank flow as well to decrease downstream flooding. So you can actually basically create a channel that is two parts. One would be the primary channel, the other one would be the overflow bank area. Okay, and this would be something that could address what would happen when you have overflow into a natural riparian area. Okay, and so it looks something like this. You have your compound channel, you have your primary channel that is deeper, and then you have, okay, your overflow bank area. And it can be either flat or it can have a rising, essentially channel bed. All right, but again, this would be essentially a situation you would have flow going down the main channel. Eventually, it will top out and start flowing over to essentially the overflow bank area. Okay, so this would represent what you'd see under a natural situation with a riparian area, with a buffer area. We talked about this before. You can change the input parameters for a channel to represent different management actions, channel improvements. Okay, for example, cleaning a channel, something they do in urban areas on a regular basis, that would change the Manning's end. You would be removing debris, moving essentially logs out of the channel, or in an urban area, shopping carts. Channel stabilization, it would change the shape as well as change the Manning's end, as well as changing the amount of infiltration. This would be zero hydraulic conductivity for this channel. Okay, soil cement, sediment source. Okay, again, you'd have no sediment coming from essentially from the banks in this situation either. It would be 100% armored. Okay, channel hardening, again, it's very simple as channel stabilization. Okay, the impacts would be increased velocity, decreased storage, decreased transmission losses, increased flooding downstream, increased channel scour downstream, okay, as well as loss of habitat. So again, these are things that you can do. If you're going to see a project where you're going to go out and clean the channel, or you're going to stabilize the channel banks, or go in and harden the channel, you can model the impact of that action. All right, Yoga, I'll let you talk about this.
Thanks, Phil. And if you don't mind, I'll have you scroll through the slides as well.
All right.
So the motivation behind creating the AGWA Urban Tool was Kinross was really good at modeling the smaller watersheds, and it had some functionality which was still not in AGWA. where we could represent urban areas in more detail. So part of my master's and PhD work was trying to get that functionality into AGWA, into the GIS framework. So use the Kineros 2 model, use GIS, and start representing urban areas in these two softwares. So the goal of the urban tool is to model each lot, your house, the roof, the driveway, front yard, backyards, and pools as well. And then put it all together so you can run a watershed analysis on a smaller scale. It could be a neighborhood, it could be down one street, it could be a subdivision, or you can also go to larger areas of urban areas, or even the whole urban area, but then it becomes more data intensive. At larger scales, when you start going above the lot scale, the AGWA urban tool lets you customize the routing involved in the urban area. So it's a point and click mechanism where you, as the user, supply what path the water is going to take. So in existing systems, you might already have an idea how the water flows, or if you're developing a new system, this is where you get to play around in terms of how you want to route the flow in your upcoming subdivision. You want it to go down the streets, where do you need to put an underground sewer system, and then where will the outlet of all that water go downstream somewhere as well. So the user gets to decide what that flow route is going to be and give it to the tool. And since we're working at such a small scale, we also wanted to focus on green infrastructure practices, and three in specific: retention basins, permeable pavements, and cisterns that capture water off the roof. So we included that functionality in it as well. And it follows the same process similar to the other tutorials you've worked, where you start by putting a geodatabase together, then start discretizing your elements, put in the parameters, create the input files, provide the precipitation data, run the model, bring the results back, and then view the results as well. So it's the same set of flow, similar to the original AGWA tool, but it's a separate add-in now. Phil, if you don't mind, can you go to the next slide, please? So the Kineros 2 model has an urban element, which is shown on the right with all those different colors, that can discretely model various impervious and pervious areas in different combinations. So there's a directly connected pervious area, which just says that is a small element in the urban element, where if the water falls, you can set a KS value to allow the water to infiltrate. And once that infiltration capacity is reached, the water will flow over into the street. So all of the overland flow goes towards the street from the lot and then down the street as it follows the route on the street or in the neighborhood or in the larger watershed. But with these smaller areas, now you can start representing these discrete elements on our lots. So in the case of AGWA, what it does is it uses the indirectly connected impervious area to represent a roof, the connecting pervious area to represent a front yard, the directly connected impervious area to represent a driveway. Non-contributing areas can be used to represent pools where the water never flows out. It's a sink. It could be a sink in your backyard as well. And then you can represent half of the street in front of the house. And along with this, green infrastructure practices are represented similarly as well. So any water that falls in the indirectly connected impervious area can be captured into a cistern. And once the cistern fills up, it starts to overflow and will flow into the connecting pervious. And when the infiltration capacity of the connecting pervious is met, the water will flow into the street. And all of the other elements give you the functionality to put a retention basin at the end of it. So you can provide a depth, a volume, an infiltration rate. So any water that flows off that subcomponent goes into the basin. Once the basin fills up, it's also infiltrating at the same time. But once it starts overflowing, the water goes into the street. The directly connected impervious that is used to represent driveways can be given a KS value to indicate that it could be a permeable driveway as well. And then the street can have a KS value to indicate that the street itself can be permeable as well. And then the street also has a curb cutout section, which is similar to a retention basin on the side of the street. So the water can flow from the street into the basin first, and then once it overflows, it'll go down the street to the next element downstream, basically. In general, the Kinross to flow route assumption is on the bottom left, where water will flow from a lot down the street, and then it'll accumulate down the street as the water comes from all the adjoining routes to the lowest part of the watershed. It still uses all the equations that Kinross 2 offers. So the kinematic wave equations are still used in order to route the water. But instead of the plane and the channel components, you use an urban element. So when Dave was talking about the power file and how everything is represented using a plane element, a channel element, in the case of the urban component, any lot that you want to represent is represented by its own element called the urban element. And you can still include planes and channels, but the functionality in AGWA is only restricted to the urban element. So if you want to include all of that together, then that's something where you'll have to open the power file and start modifying things in there. You can go to the next slide, Phil. So as part of the tutorial number 13, where you're assessing the post-development effects and the impact of green structure in Sierra Vista, you're looking at this watershed, basically. So when we developed the tool, we tested it out on this watershed, which Dave mentioned before as well, which had good instrumentation in terms of gauges and weirs on the inlet and the outlet. So we had good data in this watershed that we could use to validate how the urban tool would work once implemented in AGWA. So we have 66 residential parcels. They are very similarly built, and we decided to do 3 types of analysis. One, understand how the water is coming off the streets, which is 2.27 hectares, around 16% of the total area of the watershed and 50% of the total impervious area inside the watershed. We also decided to do a roof runoff analysis. So we put in a 38 cubic meter cistern on each parcel to capture any water that comes off the street. And we ran the model for 10 years, or we ran 10 years worth of precipitation data to understand how the cistern would fill. We set up conditions on how it is emptied and what happens when the cistern fills up as well. And lastly, we wanted to try out different GI scenarios, where what would happen if there was no GI practices on each of these parcels. What would happen if there was one retention basin on all of them, if all the driveways were made permeable, and if we had a cistern on all of the parcels. So we ran those scenarios as well. The link at the bottom is to the paper that we published that came out of the study. But the next slide will show you the results that we have. So Phil, if you don't mind, can you go to the next slide? So if you look at them one by one, on the right to the top is the roof runoff analysis. In Sierra Vista, most of the rainfall is high intensity during the summer, and then in the winter, it's more low intensity, larger duration rainfall. So we noticed that most of the volume that we could capture of the roofs was during those summer months from July, August, and September. There was still some capture, but the rainfall volume itself wasn't enough to capture a lot of water to begin with. But then we compared it to the per capita water usage in Cochise County, which Sierra Vista is part of. And that's that black line, which indicates how much that average water usage is on a monthly basis. So definitely for the summer months, the roof runoff that we capture can meet those per capita water demands. And if we can store that water long term, you could potentially use all of that water to meet the demand throughout the year. But it involves storage and water treatment as well, based on how you want to use the water. So this was just a hypothetical scenario that could help inform whoever's living that, hey, if you size the cistern correctly, if you have a large enough roof area, you might be able to capture all this water that you can use to supplement your water use. And then you don't have to rely on the city for that much water, and you're paying less bills in terms of how much water you're using as well. So that was the roof runoff analysis. On the bottom right is the street runoff analysis. And we wanted to understand how much water is just coming from the streets, because the streets is a highly connected impervious network. At least on the parcels, there are pervious areas where the water has a chance to infiltrate before it starts accumulating. But on the streets, any rainfall that falls on the street is just going to go downstream as fast as possible. So what we found was more than 45%, and 45 is the lowest in the month of June. that most of the runoff coming out of that watershed was off the street. And in some cases, it was more than 70% as well. So if you are a planner trying to figure out flood mitigation, you will need to target the streets in order to either capture this water so it can be used locally, or divert this water downstream to either a larger retention basin or a detention basin for that matter, or to the nearest wash or channel as well. But in the summer months, when the volume of water is larger as well, the water coming out from the parcels, it can meet the same amount of water that's coming off the street. So that was a very interesting analysis that came out of that as well. And then to the bottom left is the analysis of the different scenarios. So we wanted to compare, we wanted to look at the difference between what would happen if we put in GI and then compare it to what would happen if there was no GI in the first place. So the basic takeaway from that was depending on the size of the GI practice that you can put, in the simulations, we can put any value we want to see how it would react. But turns out in a similar comparison between the 3 GI practices, the permeable pavements, the retention basins, and the rainwater harvesting systems, retention basins were doing a better job at reducing the average runoff volumes coming out from each parcel, and mostly because they have a higher KS or infiltration rate. They have also storage capacity at the same time, so it's double the benefits. But then the only caveat is that you need to have that much room to dig out a basin in your yards to capture all of that water. Driveways and rainwater harvesting was limited because the size of the driveways was very small on each of these parcels, and the size of the roofs was smaller compared to the entire lot. So the water that could be captured out of them was not as high as, say, a retention basin, which was able to capture all the water that's coming off the lot. But these practices seem to be most effective during the summer months, again, when the total volumes were larger as compared to the winter months. So that was the Sierra Vista case study. Recently, we've also done some case studies in the city of Tucson, in the high school watch, which includes the university. And we have some published papers about that as well, if anyone's interested. But in tutorial 13, you get to play around with this tool. Just keep in mind that this tool is not part of the original add-in. So if you want to run that tutorial, you will have to install the urban add-in separately. And you may want to delete the original add-in and install the urban add-in. But let us know if you're planning on doing that, and we'll give you those detailed instructions. But that's it from this presentation. I don't know, Phil, if you had any concluding remarks, or Shay.
No more remarks from me at this point.
No, but are there any questions?
I will send the links to the papers. There's a question in the chat that wants the links to the papers, and I will give you those links right now. Let me just grab them. Yeah.
So a number of the tutorials use one or more of these tools that we talked about. Okay, so there is a tutorial dealing with the urban toolkit and so on. So if you're interested, take a look at some of these. Essentially, if you're interested in any one of these tools, you may find essentially a tutorial that really addresses them specifically. I know we have one for basically the ponds as well. All right. And post-fire. Anything else? Do we any other tutorial that looks at specifically, Shay, I'm talking to you, that looks specifically at one of these tools?
I need to pull up the.
Yeah, I don't have it in front of me either.
Yeah.
That's why.
Just a second. Let's see. What did you ask about, Bill? If there,
I know we have a tutorial that deals with ponds. We have a tutorial that deals with post-fire. We have a
Yeah.
tutorial that deals with urban.
there's definitely tutorials that are not here that we have. For some of these tools, like we had some for that military training disturbance tool that are not included in the training package. We do not have one for the stream buffer tool because that's still, it hasn't really been distributed yet with AGWA, but it's, it's available. Let me see what else. There are others. The wetland kind of scenarios and diversions, those are, I think, in tutorial. I don't remember. I don't have the numbers of the tutorials in front of me, but most of the things that you covered are included in the tutorials. There are a couple that are not, though, like the military disturbance tool and the stream buffer.
Okay. All right.
Are not included in what everyone has.
Well, if there's no questions, we'll take a break.
Yeah, we'll take a break until 2 or
Till
12.
2 o'clock when Dave will talk about post-fire.
Yeah. I'll put up a little slide placeholder until then.
All right.
Just a heads up, if anyone's starting on the urban tutorial number 13, just be aware that when you set up the first step or the geodatabase, just make sure there are no spaces in the folder names or in the whole path, because it can cause some issues down the road with some of the tools. So just be careful not to put any spaces when you name the folders.
Well, welcome back, everybody. We'll give it just another minute or two to see if we get any more people into this Zoom room. Okay, we'll go ahead and get started. This last presentation is an overview of AGWA for post-fire watershed assessments. Let's see, I'm not able to advance. Oops. Okay. So how did we get here in terms of having relatively widespread use by the Department of Interior bear teams for using some of the AGWA tools to look at post-fire watershed assessments? And some of the premises that we came up with in terms of analyzing a watershed or two that had good observed rainfall and runoff data both before the fire and after fire is that we found changes in hydraulic roughness can explain much of the post-fire hydrologic and erosion response in non-hydrophobic soils. So AGWA provides a framework to quickly parameterize watershed models and visualize the results. And we can quickly provide watershed scale assessments for both runoff, erosion, and sediment transport at multiple points of potential risk and for all model elements, including those downstream of burned areas. So in 2011, on the Wallow fire in northern Arizona, very, very large fire, almost 500,000 acres, AGWA, with a lot of help from Shea, was the only model that produced results for the entire burned area. And then in the process between 2012 and 2015, it was used in 21 large fires. And after that, it was adopted by the Department of Interior National Bear Teams. And we defined model parameterizations for post-fire. So we defined lookup tables for pre and post-fire parameters. So the pre-fire parameters are just what you've been learning about in terms of how we use DEMs, land cover, and soils to set up the pre-fire model. And now from a post-fire model, we look again at a function of land cover and burn soil severity from well gauge basins. And given this soil severity, burn soil severity, we adjusted curve numbers and roughness in the SWOT models. And in a Kinross 2 model, we adjusted roughness, interception, cover, as well as the saturated hydraulic conductivity. And this is the rules of thumb that were suggested by Pete Robichaud of the Forest Service, that if you had a low, moderate, or high severity, you would adjust the cover by these percentages, 15, 32, and 50. And we note that K2 does reduce as a function of cover. And again, that will decrease the infiltration rates. And so for K2, we set the roughness factor for overland flow on bare soils, or to a bare soil N value of 0.011. So that's really more than an order of magnitude change from an extremely rough environment that would have existed pre-fire. That's a conifer forest with a lot of needle and debris litter on the ground. So typical application of AGWA by the bear teams, just a little bit of background. So bear teams have to come in and complete an assessment within 14 days. And that's specified by statute so that application for emergency stabilization monies has to be made with this time frame. So the first thing they do when they get to a fire is talk to the local land managers and identify values at risk. And again, values at risk might be visitor centers, campgrounds, archaeological sites, road crossings. And so what we can do with the feature that Phil noted is that we can force a discretization to the values at risk. In other words, we'll get a point shape file, as we can see over here, and we will make sure the model discretizes to those values at risk. And those are the yellow triangles here. And so we'll get a report on both flood and erosion at those locations. And because of the time factors and the way we've set up AGWA, the bear teams usually get notice that they will deploy in 3 to 6 days to a fire while the final suppression is underway. So they have time and they know where they're going. And if they've talked to the local managers, they can identify the values at risk, and they have everything they need for a pre-fire watershed response with a design storm. So again, use the available National Land Cover data, DEM, and the soils to run your pre-fire case. So the first product that they get from both USGS and Forest Service is a burn area reflectance map, or the BARC. So they can do an initial simulation, post-fire simulation, to stratify field work and produce field verified burn severity maps. So, in essence, this gives them an idea of where they should go to in the burn area to do their checks. Now, this is part of their process, is to do a field verification, but because of the first initial post-fire simulation with the BARC, they may select different areas to go to and actually do a field verification. So once they've done the field verification, they produce a verified soil burn severity map. And then again, you can simulate post-fire with the verified burn severity map. And again, you do the pre and post-fire simulation and do the differences of those and either percent change or quantitative change. And so again, this allows limited resources or stabilization funds for fire mitigation to be applied to the highest risk areas. And in the case of the elk fire in Idaho, they saved roughly $7 million. So their default position is that if there's an area that shows severe or highly severe burn area, that some action will be done to stabilize it. So again, this is what we have and some of the changes. So this is the mountain fire near Palm Springs in 2013. And this is the difference in both peak flows in percent and sediment yield for a color ramp. Again, the brighter blue and fatter the channels, the higher percent change. And then with the overland flow elements, the darker the brown area, the greater the percent change in sediment that's shown here. So the design storm that was used was a 10-year, 1-hour event, which dropped 1.26 inches of rain. And this was the initial burn severity map that was used for this watershed. And, you know, unsurprisingly, those areas of severe burn area in red and somewhat in yellow caused the biggest response changes in a local level. But what also is important that you can do with AGWA is see if those changes that are quite high at a local level persist downstream. And, you know, if they're attenuated relatively early, you may have to do anything in terms of protecting this road culvert further downstream. So again, this gives them a guidance to say, all right, where should I spend my dollars to increase culvert sizes, put seeding down, and that sort of thing if needed. So here's another fire, the Las Conchas fire in Frijoles Canyon at the Bandelier National Park. And this was a complex, a large complex of fires and burned a number of watersheds in northern New Mexico coming off the Bandelier Plateau. So Frijoles Canyon is this one here. And you can see quite a large area of severe burn severity. And again, we're doing pre versus post-fire simulations for a 25-hour or 25-year, 6-hour storm. And their main value at risk here is a relatively newly built visitor center for the National Monument that is literally just off the stream area for this. So the hatched areas represent where rainfall was placed, both pre and post fire. And again, we see the high burn severity sort of in the, you know, the upper 20 to 40% of the watershed. And again, that's giving us a large response in terms of percent change in watershed peak. And in this case, you can see we still have pretty large response in the channels. It dissipates some, but this gives them, again, an initial estimate of how large the peak is near the visitor center. And, you know, do they have to protect that visitor center with sandbagging or those concrete K-rails? And again, this is what we found from the pre and post-fire modeling in terms of overall percentage changes. You know, and the bottom two are the hyedographs, the design storm hyedographs. They're the same in both cases. And runoff. And again, pre-storm, pre-fire runoff, quite low. So we got a big increase in post-fire. And then also in sediment yield. And this was a useful way to again, for the local emergency managers to display the relative impacts and the locations of those impacts. So there was a recent study that compares pre and post-fire modeling results for four different methods on this. One is a rule of thumb, the ROT, which is really has to be informed by local experts. The modified rational method, the HEC HMS model with curve numbers, and Kinneros in the San Dimas experimental watershed. And that publication is Chen et al. 2013, and I'm pretty sure that's on our website as well. And the results, are summarized here that both the rule of thumb and the modified rational method were okay with careful local calibration. And again, nothing against this, but do you have, very experienced personnel that have a good idea of how model response or watershed response will change with severe burns? The curve number method in HEC HMS operated better for pre-fire prediction, and Kinneros 2 did better for post-fire predictions. And they hypothesized that there was evidence that the pre-fire runoffs is saturation excess modeling or subsurface flow, and that the post-fire mechanism is infiltration excess, or where the rain rate exceeds the infiltration rate. So Kinneros 2 only does infiltration excess with a single soil layer, but can do saturation excess from a shallow soil over rock with a 2-layer representation. So you have to go into either hopefully have local data, or AGWA does not automatically set up, let's say, a second lower soil layer. A number of assumptions have to be made about thickness of the upper levels and that sort of thing. But so what they propose is happening that pre-fire, you've got, again, a lot of litter cover, a lot of ground cover, and that you'll have infiltration on site that might typically go down, hit a restrictive layer, and then laterally flow to a channel. So this is a slow response and a very attenuated peak flow rate. And again, this is typical in unburned areas with shallow soils and heavy litter. In a post-fire situation, again, we get runoff generation in infiltration excess where the rainfall rate or the rainfall intensity is greater than the soil infiltration rate. And again, this is more typical in burned areas with high intensity rates. And in a saturation excess case, you do get, saturation of all the pore space, which eventually does lead to surface runoff generation. And again, this is more typical in wet areas, shallow water table, or shallow soil over rock. And again, they're saying that this seems to be better represented by the curve number. So, how does this hold up under looking at some actual observed condition? So this is the Marshall Gulch watershed, which is just north of Tucson in the Catalina Mountains. And they did have some, very good pre-fire data. So this is a pre-fire hydrograph on August 18th to August 26th, 1957. Big fire occurred on the 24th of July in 2003. That was the Aspen fire. So take a look at these hydrographs. Now the storms are not the same, but they're not that much different. You know, this storm, average storm depth, 54 millimeters, runoff volume, 10 millimeters, runoff to rainfall ratio, about 19%. And the QP is quite small. Now contrast that to the observation post-storm or post-fire. So look at the kind of long-term base flow conditions. So they were still getting watershed response almost over 10 days. And note the difference in the extent or the maximum number on the y-axis. So 0.16, very low rate. Contrast that again to the post-fire situation. It's up at 40 millimeters per hour. So that's, you know, well over, let's say, a couple orders of magnitude. And also note that all of the runoff response is basically done in about 3 hours. So we've decreased the response time due to the fire from about 10 days to 3 hours. The peak rate increased greatly, a couple orders of magnitude. And again, 0.16 versus 41.4. So, you know, the runoff to rainfall ratio is similar, but the timing and the peak rate are profoundly different. And again, we're able to, again, reproduce this by cutting down the hydraulic roughness term to a very large extent. And basically the idea is that we feel a whole bunch of that litter and much of the vegetation is burned off. So when the rain falls, it'll come off much more quickly. Another graduate student, Gabe Sidman, investigated, you know, how should rainfall, you know, be input to the model. So again, we often after a fire, you know, we don't have a rainfall event. It may occur, of course, sometime in the future, but the Bear teams have to do their assessment in 14 days. So, you know, initially we said, let's take a design storm and let's put it over the whole watershed. Well, that typically puts a lot more water on the watershed than might be observed in a typical thunderstorm or rainfall environment. So, you know, the modeling goals are, you know, can we accurately predict or reproduce the magnitude of an event? And can we predict which stream reaches and hill slopes are at risk? So what's the best way to represent the rainfall to meet these goals or objectives? And in this case, Gabe looked at 2 fire events, one in Zion National Park, August 1, 2007, and then back to that same fire we just looked at in the Frijoles Canyon with an August 2011 storm. So again, here are the burn severity maps. And we can see smaller area was burned as a percentage of the overall watershed. And this one, a relatively large percentage of the area was burned with higher burn severity. And again, this is our outlet point of interest. And the visitor center is right here. And I'm not sure why this was chosen as a value of interest or a modeling location. So can we reproduce the post-storm flood magnitude? And, you know, again, give us some idea of the best representation. So we were fortunate enough in both of these watersheds to get pretty good radar coverage. So we could use radar coverage to input into the model to look at post-storm response. So the green hydrograph you see over here is from the actual storm as recorded by the radar. So, radar, there are differences between radar rainfall estimates and rain gauge estimates, but we didn't have a bunch of rain gauges. So this gives us a pretty good indication of what happened during the storm and where it happened. So we applied uniform rainfall intensity over the entire watershed, which is typically what you do with a design storm. You might use area reduction factors, but for a quick read, this is the way to do it. We used an SCS type 2 storm over the whole watershed, which gives you a peak in the middle of the storm. So here's the uniform rainfall case in blue, and here's the type 2 storm, the red, and here's the type 2 storm just over the burned area. And again, they give you a HIETA graph that again has got a peak somewhere in the middle of the storm. So that's what these input hydrographs look like. And again, this isn't a hydrograph. This is a HIETA graph from the radar. So now let's take a look at the results. Here's what the radar looks like over the Zion area. So these are color ramp again of the rainfall depths, total depth of the storm. And we can see we've got some heavy rain over part of the burned area and, lighter to medium rain elsewhere. And so the proximum duration of the event sensed by radar was 1.5 hours, and it dropped about 30 millimeters of watershed. And this, if you go to the NOAA 14 information, correlates pretty well with a 10-year event. And here's where the results are. So they did not have gauging stations at the outlets of either of these watersheds. So typically in a case like this, the USGS will go in and make an indirect measurement to try to estimate peak flow using high water marks. So at North Creek, we can see using the radar, and these are the hydrographs from the model, that using the DHR radar rainfall estimate, we almost get to the lower band of the uncertainty level for North Creek, and that the uniform type 2 and type 2 over the burned area are shown here. So in the uniform case, we're not generating any runoff, but the best match appears to happen with the type 2 burned area. So that's the purple one. So when we go to Frijoles Canyon, we have a slightly more uncertain USGS indirect measurement, 25%. And we can see that the radar estimate falls right in that band. And there's little difference between type 2 area on the burned area only versus on the watershed. And that's frankly because most of the watershed burned. Again, the uniform is much lower on that. So, our initial indication is, well, it looks better if we use the type 2 on the burned area only. Yeah, and there's again, our radar estimates are very good. So here's the visitor center at Bandelier after the fire, and you can see all of the sandbags stacked over here where they were put up to help protect this visitor center. But now we're going to ask the question, does the rainfall representation change the model's prediction of high-risk areas? Even though we saw that the rainfalls from these design storms gives a much different answer than the actual event as predicted by radar. So again, for a rapid assessment, a design storm is used. And in this case, it was a monsoon storm, 2-year return interval, 30-minute storm that would drop an average of just over 13 millimeters. So which hill slopes and stream reaches have the greatest change in runoff or sediment and yield from pre to post fire? So these are, again, the color ramp results from the hill slopes and the percent change in peak value. Remember, the burn severity area is down in this lower portion of the watershed. And again, you can see that's where the action is happening in terms of changes, both in runoff and sediment yield. But again, we're going to, put the rainfall on under these same 4 cases that we've been talking about on this event. So here's our map of high risk areas, both for the North Creek and Frijoles Canyon. And here we've got a little blow up down here. But now let's rank them. So we can rank the impact of either runoff or sediment on every element and say, which is the highest one to the lowest one. And in both cases, we do that. And so this is a ranking due to the fire response, again, from highest to lowest percent change. And there's a Spearman's coefficient statistic that can allow us to statistically compare rankings. So if this coefficient is 1, it implies perfect agreement in the ranking. So again, you develop a ranking for each type of rainfall input. Monsoon, this is the radar one, uniform, type 2, only the burned area. And we're going to compare the rankings under these different rainfall scenarios for peak rate on top and peak flow rate for sediment yield. And okay, so the brown is the rank comparison for sediment yield on the hill slopes, and the blue is for peak flow on the stream reaches. So if the area is, or if the ranking agrees well, 0.9 or 0.89 and above, it says, it's just about as good as applying the actual observed event. And we can see here for sediment, we get very high agreement, not as good for the peak flow. Our lowest, I guess, is 0.46 here. And down in Frijoles, again, we get pretty good rankings in terms of the Spearman coefficient. But the point is, the statistic is generally high for the design storms. So our conclusion is that the rainfall representation drastically does change our ability to accurately present the model post-fire storm magnitude. And we've shown in this study, or Gabe has shown in this study, that radar is the best method to do that. But that the high risk areas, the predicted high risk areas, do not vary drastically between the rainfall representations. So the overall conclusion here is that AGWA Kinross can be used to reliably predict relative pre to post fire changes, and again, identify these areas at risk. And again, models are more reliable at predicting relative change than absolute change. So we've talked about this over and over again. You need good rainfall representation, and we've suggested to the BEAR teams now that there is getting a bigger repository of, storm conditions that are recorded with radar, that it may be better to go back into the radar rainfall record and, pick a storm that is, a relatively large storm to test this. In other words, don't make all the assumptions that you do with a design storm, but use something for radar that will give you the actual space-time changes in an actual event. And we haven't automated that sort of selection process, but we really think this is the way to go. So again, our lessons learned from the bigger applications is that using a design storm with uniformly distributed precipitation will accurately identify the ranking from pre to post fire. However, when I say uniformly, it's in space. It's not uniform or in time, because we saw that very much under predicted. So we also saw that the Bear team benefited from the initial results. In other words, using the BARC predictions in terms of helping them prioritize their field work. And that, again, these percent difference maps can help the Bear team locate values or risk levels and optimize or better optimize the design for treatments. And this has helped other agencies in terms of the Corps engineers, statewide hazard planning groups, again, identify site-specific modeling needs for emergency warning systems. And I think that's all I have. Are there questions? Everyone's quiet or very tired. And again, there's a couple of papers. Sidman is the first author on these. And again, these are on the AGWA website too, if you would like to look at them in more detail. Now it's time to go back to our last block of time for tutorials. But if you have to drop off, we would really encourage you, before you do, to take these quick surveys. And again, one in terms of how well did the training go, and another one in terms of what is the best way to do our training. So please do that, and type in any other suggestions or comments you might have in the meeting chat. And again, we'll come back at what, in 2.5 hours? No, take that back. Where are we at?
Dave, I was thinking that maybe we do that now in case people
sure.
didn't want to, if some people are not going to be doing the tutorial, so that they, just with all the time zones, we could do the wrap up, and then we could stick around after the wrap up to work on the tutorials for people, but also give them a preview of the ArcGIS Pro version.
Yep. So do you want to go into the ArcGIS presentation right away and then talk about things, or talk about things now?
Yeah, I'll just kind of show people what the ArcGIS Pro version looks like first, and then we can have a little bit of discussion. And then after that's over, if people still want to work on the tutorials, we'll stick around, and then otherwise people are free to leave when they need to.
And if you didn't get through all the tutorials, or want to do some other ones that you didn't select, you've got everything you need to work through those on your own time. And again, if you have any questions or hangups, I guess I direct you first to Shay, and then he'll distribute your questions. So let's say Yoga, if you have more information or more questions about the urban tool, for example. On to you, Shay.
Yeah, I'm going to see if I can get this screen share working. Hopefully the screen share doesn't crash. I haven't had the best of luck in the last couple of days with this. So if people haven't heard, the writing is on the wall that Esri is moving away from ArcMap and pushing everyone towards ArcGIS Pro, and we're adapting and doing the same thing with AGWA, and there's other kind of motivations as well for recoding this. But in doing so, it allowed us to pivot towards ArcGIS Pro at the same time. So things are going to look a little bit different, both in terms of the UI and of AGWA, and then also in the way that data is stored that AGWA creates. So if you're not familiar with ArcGIS Pro yet, if you're a GIS user, you should probably start getting familiar with it if you're going to be using Esri products. The basic idea is the same in terms of having a map view, having your table of contents, and then kind of having a catalog pane that has your data. There are quite a few differences in the way these are all done, but essentially what we're doing with the next version of AGWA is creating it as a Python toolbox, where every tool that was available in the drop-down menu before is now going to be available as tools in this toolbox. So what I've done is basically we can start this with an empty map to show the process from the beginning, but basically in the empty map, I've added in the data, and I'm just going to copy it over from here. I've added in the data I want to use for my modeling. Some of this I've already created, so I'm going to get rid of that. So basically, I've got my DEM, which I've symbolized kind of with a hill shade and color ramp. And then I've got a bunch of DEM derivatives that I've already created that we're going to use to kind of set up the whole workspace for AGWA. So the first step is not actually delineation. In ArcGIS, or sorry, in ArcMap, we saved the AGWA directory with the map project itself. Now we're kind of saving the AGWA directory in do these pop-ups show up when it opens a new window?
Yeah, we can see it.
Okay. So now we're storing all these input data and the data directory, or sorry, the AGWA directory, the pointer to the AGWA directory anyway, with the geodatabase that will store the delineation and the discretization and all the input data. So that's one kind of small change there. The next change you'll notice is this delineation workspace. We're creating a file geodatabase for to save that workspace in without actually creating the delineation. So the reason for that is we want to be able to automate some of these steps and store some of the metadata with that geodatabase, and then also store multiple delineations within one workspace that has all of the metadata defined for how that delineation was created. So here I'm just going to do a demo. Already got one that's this date, but I'll just put in a second one here. So now I've created an empty file geodatabase. And then after that, we're going to select the input rasters that are associated with that delineation workspace. So these are some of the same inputs that are filled in the first step of the version that you've been utilizing so far. But you'll notice that we're also supplying a few additional rasters in this case. Got a slope raster, an aspect raster, and a flow length raster. Before we had, our DEM, our flow direction, and our flow accumulation. At this point, we also have our unfilled DEM, if you have that available to you. And the reason for that is if you used the like the pond tutorial, or if you're doing slope calculations, the slope calculations would be probably more accurate in an unfilled DEM, especially along the channel, if there's any filling that's happened in that drainage. So setting all this up, it's basically just pointing to locations where the data is. And all this is really done. It's not what I meant to do. Is created a table in that file geodatabase that I just made, which again, if you remember, it was demo 2022-11-16. So now I've got this table that was just created. And this table is what kind of defines this as a delineation workspace for AGWA. And it would open. You'll just basically see all those parameters that I supplied, the path and the names of the data that I supplied in that first step. And that's two things. We were storing that information in the current version of AGWA, but we weren't allowing you to see it. So this kind of gives you a pointer to it where you can see what is actually being stored, what you use to create the AGWA outputs. You'll see that if I go back to this step one, I've got a red X here, and that's just telling me that I can't use this name because I've already created a workspace there in that name. You don't want to overwrite something that you've already done. So after you've set up the workspace, the next step would be delineating a watershed. So you select the workspace that you created in the first step. And notice now that I don't have to define my DEM, my flow direction, or my flow accumulation rasters anymore, because they're pointing to that metadata table that we had before. Here I'm going to select a point it's already been selected here in this watershed, and you can see that the selection is already being reflected in the interface to let you know that there is a selection. If you have a feature class like this that has a bunch of points in it, if you don't have a selection made, there'll be validation to make sure that you don't proceed without creating a selection, because otherwise we wouldn't know which one of these points you wanted to use. I don't think I need a snap radius for this particular point because it already lies on the stream network as defined by the flow accumulation grid. And then I just need to create a name for this, which I'll just call it Flume 11. What we're looking at here is just this is the Walnut Gulch Experimental Watershed in southeastern Arizona, and these are the flumes and sub watersheds. What the points represent here. So really, yeah, it's just defining your workspace and then your outlet and a name for your delineation because you've already done all those previous steps. And when these are running, you'll see, if you open up the view details, you'll see all the different steps that are happening here so that you can get an idea of how far along in the process you are. All right, so we got our watershed delineation. Again, I have a red X here on the tool because I already just created this. I'd have to change the name if I wanted to run it again because it doesn't want you to overwrite an existing delineation in your delineation workspace. So the next step, like in the AGWA 3.10, is discretizing that delineation. Many of the same inputs here. We haven't implemented all of the functionality that's present in the current version, but here we'll just do a flow length discretization with a threshold of 1,000 meters. And we're going to use any internal pour points. I'm just going to call this zone 11 with a flow length of 1,000. And again, you can see as it's doing the processing, kind of all the steps that are being performed in the background as part of the discretization. One of the nice things is when we created that, when we supplied that flow length raster in that very first step of defining the delineation workspace, that avoids us having to create that flow length raster anytime that you perform a new discretization that uses the flow length threshold methodology. So by defining some of those inputs up front, it avoids having to recreate them every time we do a new discretization or a new parameterization. Again, we can't, there's a red X here after we've successfully performed the discretization because we don't want to overwrite an existing one. Step after the discretization is a parameterization. Again, many of the same inputs that you see in the current version of AGWA. And what the other thing that's happening with each one of these steps is we're creating additional metadata tables to store all the input parameters. And again, those were being saved in our in the current version of AGWA as well, but they weren't being shown to you. So you had to keep notes yourself of the different inputs you used for the different discretizations or parameterizations you had if you you know, wanted to go back and see what you did in the past. It required you to kind of maintain that documentation yourself, and now we're putting it in just kind of a more accessible place to take a little of that burden off of you. And in each one of these tables, you'll basically just see the inputs that went into creating that particular delineation, or in this case, that particular discretization. And again, parameterization. So the other thing that's different here is because we're storing this in rows in this table, we could create multiple delineations in this single file geodatabase. And the only thing that would be different would be the name and the outlet location, because they're all still pointing to the same input data sets. So that's just another kind of improvement, I would say. And then we're just working through every single step that kind of is implemented in the current version. supplying land cover. I need to go and grab my lookup table. So in this case, we're using GSurgo data. So I mentioned it yesterday. With the GSurgo data, all of the tabular data comes pre-populated in that database. So that's a little bit of that's a plus of using GSurgo data. And then, so this is the second part of the parameterization. The first step was that element parameterization. To do a land cover and soils parameterization, we have to select an existing element parameterization to complete the whole parameterization process. And we can kind of see the details as it works through it. Another perk of kind of creating all of this in these tabular data sets in terms of the metadata is that it allows us to create these tables outside of AGWA. You could create really a batch run of delineations and discretizations and parameterizations by supplying the input data to those meta tables and then calling the functionality to just basically loop through that table and create all of the different, basically all the different entries that are in there. There are some nice improvements in ArcGIS Pro, but there's also some, it seems like there's a little bit more overhead with the UI and with running some of these tools where there's not quite the, I don't know, the performance, I guess, with we were hoping for, but we're still early in this process. So there's a lot of benchmarking and hopefully some more improvements that we can do to speed this along a little bit.
Hey Shay, I just have a quick question about the Arc Pro version.
Yeah.
So when you were on the very first step, selecting your flow accumulation rosters and your stream roster, in the ArcMap version, you can create it within the AGWA Kinross platform. Can you do that in the Arc Pro version as well, or do you need to have those beforehand now?
Basically, if you supply a DEM here, and if it's not been filled, then it will fill the DEM, create the flow direction raster, and create the flow accumulation raster, create the flow length up raster, and then save all of those data sets in the delineation workspace that you're creating. So basically, all of these parameters will, if they're not supplied, will be created and saved and kind of pointed to in the workspace. Did that answer your question?
Okay. Yeah, definitely. Thank you so much.
Okay. Yeah. So a lot of this, it's the same kind of same inputs. So in that sense, it'll be familiar to you. We just weren't far enough along. We don't quite have enough validation on preventing you from inputting invalid data to have demoed or to have given you this as a play around with. So we're not quite ready to share it yet. But we're at least happy to show you that it's well along the way and will be coming soon. So this step was creating the preset files. So if you recall, those are text files. Those again kind of get output in the same output location as where your workspace is. So here it would be in this Flume 11 folder. And there should be a preset folder here, and we can't see it here, but if we navigated to this window in File Explorer, we would see the file that I just created with the precip step. And then last step that we'll just showcase here is just writing the input files. This is going to be a little bit different than the current version. If it doesn't crash on me, where we're going to write the parameter files in a separate step than writing a simulation, which basically allows us to create a folder for parameter files and then create a simulation by selecting from those parameter files and selecting from the preset files we've written. It looks like ArcGIS Pro is not it's doing what Esri products do and not cooperating. So I guess maybe I'll just stop there because I don't want to wait on this spinning wheel indefinitely. Oh wait, there it goes. So all we've got here in the toolbox right now, kind of numbered the steps. We have to number them to kind of keep them in order. That's it. It automatically orders the tools in a toolbox alphabetically. So we kind of want it top to bottom, but I don't know that I would have. Yeah. We have to do it the way they do it. So anyway, where was I? Oh, writing this. So this is a little bit different where I haven't updated this. That should say parameterization, parameter file name, not simulation name, but and the difference here is in the current version, when you write the parameter file, you also select a preset file and it goes into a directory for a simulation. So we'll have an additional step that allows you to select from the parameter file that you've written here and the precipitation files that you've written before, and then store them kind of hierarchically like we do the current data sets. So I could open up File Explorer, but show you those input files, but they look exactly like what you've seen in the current version. So we also have the post-fire land cover. So that's the same as the burn severity tool, and the modify land cover here is the land cover modification tool. And so those have been implemented as well. So anyway, that's just a kind of a preview of what's to come. And we hope to have put up on our website to share in, I don't know, 6 months or so. So any ideas or any questions, any suggestions that you all would have for us for things that you'd like to see in an ArcGIS Pro version? Silence.
This is your chance to really tell us how to improve this.
Well, it's also your chance to tell us how to improve the trainings for people that are sign up in the future, because I think we're going to do that wrap up now before we go back into the rooms for our last tutorial session.
Shay, there's a question in the chat.
Oh yeah, so we didn't have that shown, the results viewer. We don't have that in the pro version yet, but yeah, that's coming next. Running the simulations that we create the parameter files for, and then importing the results, that will be there. Yes.
Hi, can you hear me?
Yes.
I'm sorry I'm late, but I just got in. I missed most of your ArchiPro presentation. My experience, your training, I think is wonderful because you tutorial instruction is so clear. So basically, I didn't have any much problem. But I think in future training, if you publish your training on your website, give people like say 2 weeks ahead, then get a training together, like address people's question on the tutorial. I mean, this exercise. I think probably that's a more efficient to me. That's just my personal suggestion. Like I say, I had someone like S3 online courses too. So like say the instruction generally step is relatively less, so take more time, but your instruction basically to me is very detailed. So if I follow exactly your step, I get similar results. That's pretty clear to me. So like I say, I definitely will continue finish all of exercise. So, but I just say it's wonderful kind of instruction. Yeah, that's kind of my opinion. So thank you very much.
Yeah, well, thank you. Thanks for the feedback, and we're glad you liked the parts you did. And yeah, I think there's definitely opportunity to do things a little bit differently, or make some improvements. And yeah, I think that's a good idea about ahead of time. I think we'll need to. I need to do a better job of keeping our website updated, frankly. So some of that is definitely on me.
Yeah, but we're very glad they were clear, and they were easy to follow. So really appreciate that feedback. And again, that's largely due to Shay and Yoga, and actually a person or two or have retired that originally helped develop some of these tutorials.
Yeah, another thing, because I use ArcGIS a lot. When I try to make some map, the symbology to me is kind of a challenge to me. However, you made it as symbology, like a render, makes that map looks much better. Those things I think you definitely thought about ahead, make those kind of, like I say, that's just another detailed instruction. Your software doesn't require that, but however, because you have that additional step, make that like a landscape coverage after you use symbology, looks much better. So that's kind of all of those things. I think it's pretty pretty detailed to me. So yeah.
Good. Yeah, we'll try to do more of that. I know I was always frustrated when, yeah, the symbology wasn't very nice to look at. So
I just catch up. You last minute you say that's a new version for Arc Pro is not available yet, right?
yeah, it's not. We're not delivering it yet
Okay.
on our website, but it will be soon. You know, in the next, definitely within the next year. Hopefully in 6 months. And, you know, we may not have every feature that's available in the current version on release, but we'll at least have, you know, the base functionality there.
Okay.
And it's also, you know, the other nice thing about moving to Pro and the way we're using Python toolboxes is that the code will be, it's right there in the toolbox. So if you know Python, or if you have, you know, anything that you would like to do to do things differently, like it's, you can do it. Now it's a lot more difficult because it's compiled code that you cannot see.
One more question. I think I sent you email yesterday. You replied, maybe it's caused by my software license. I do have a like Arc Pro, but is this the software require spatial analysis? Like say our spatial analysis extension, only we have a few license. So even we have Arc Pro, but we turned off. That's is require turn on the spatial analysis, or is if I just have Arc Pro, no, Arc Map Pro professional license will be enough, or I have to turn on the Arc spatial analysis?
So there's a couple things I think in the problem that you had yesterday that you emailed me about. Actually, was something that several people encountered, where their ArcMap license versus, like, they had, everybody had spatial analyst, I believe, and that wasn't the issue. It was the basic versus standard versus advanced license for ArcMap.
Okay.
When we're creating that near table for the basically associating the pond in that tutorial to a node in the discretization is what that's used for. And that particular tool that is used to identify that requires that advanced license. I don't know if when we moved to ArcGIS Pro, if there's also any distinctions between and some of that functionality. Like, I think this is the only case in the current version where we need that advanced license. None of the other functionality requires it. And I think, you know, we'll try to avoid using anything that would require anything more than simply spatial analyst. But that will always be kind of the minimum requirement for working with the raster data during the delineation, discretization, and parameterization processes.
Okay. Okay. Thank you.
Mm-hmm. Any other feedback, or do you all want to get back to working on tutorials?
Don't forget the surveys.
Don't forget the surveys, right? And again, I'm happy to work with you beyond this training. You have our email addresses, so if you have questions or if you need help, or if you run into some problems or errors down the line with your own data, just reach out to us. We're happy to help, and we want to see you be successful in using these tools.
Could you resend that survey link, or it's in website, or where is that survey?
It's at the very bottom of the agenda.
Oh, okay, okay,
So, yeah, I think it moved on to kind of the third page, although since it's a Google document,
okay, okay. Thank you.
the pages are not all that important. But yeah, at the very bottom, I'll probably send out an email reminder, probably around the beginning of December, about 2 weeks before the surveys close, just to see if we can get some additional responses if you don't fill it out today. But really, you should fill it out today or tomorrow, and then you won't have to. We won't have to worry about pestering you. So. Well, the other thing we can do, since there's not that many of us, we can all just stay here in the main room instead of splitting off into the breakout rooms. None of them have been too busy. It seems like most people are able to work through the tutorials fairly successfully. So that way, if anybody has any questions or anything, we'll just keep it in here and let you guys continue to work, and we'll be here for we'll stay on another hour and a half, I think. I don't have the agenda, let's see. Yeah. Yeah, we'll stay here for another hour and a half, hour and 45 minutes to help you all with tutorials. So unmute yourself or use the chat box if you have anything to say. Thanks. There's not a link to the urban add-in, but it is available in the AGWA directory that was distributed as part of the training package. So you look in the AGWA folder, there's an add-ins directory, and in there you'll find the urban add-in. The major reasons to stay in Esri is our, big user base is really the federal government, I think, who basically have licenses for Esri products already. So I think that's really the primary reason. There's additional reasons where some of our goals include developing a web version, and the web version would be using the same code as the ArcGIS Pro version, and the web versions are just the functionality is much more complete in the Esri ecosystem than it would be in any other system. So all the tools are already there, to build the product.
So Shay, do we know if when we do get the web version developed, will that simplify the usability for people who don't have the licenses or aren't using Arc Pro directly?
Yeah, so there's a lot to still kind of figure out with the web version, but yeah, you won't need licensing, right? Because it's all going to be done on the web. It'll simplify some of the workflow, because you won't have to define all of the inputs. We're planning on, for where we have the web version implemented, providing basically the DEMs, everything that's in that first step, and also the base input data sets for parameterization would also be provided. So I think the room, the opportunity for you to put in your own data would be in doing any scenario that's different from kind of the baseline of whatever land cover that we have included and whatever soils that we've included with our national data sets. So yeah, we hope that it's a little bit the workflow is a little bit streamlined and doesn't require all the licensing that you'd otherwise need.